Welcome to the deep dive. Today, we're digging into something you hear about constantly in the news. How does a missile actually work? You hear these terms bandied about Iron Dome, Shahed drones, ballistic missiles, but what's really happening inside these incredibly fast targeted machines?
That's right. And our mission today really is to kind of pull back the curtain on the engineering. These are, well, marvels in a way, modern missiles. We're going to explore the physics, the ingenuity that lets them fly so fast, navigate so accurately, and then, deliver their impact. It's pretty fascinating technology.
Yeah, it really is. So when you think about a missile, it might seem like this single, complex, almost mysterious thing. But I guess like most complex systems, it's actually made up of key parts working together.
Absolutely. That's the best way to think about it. At its core, any missile, doesn't matter how advanced, it relies on four basic components. First, you've got the propulsion system. That's the engine, basically. Gives it the power to fly, to get off the ground.
Okay, the engine. Makes sense.
Then there's the guidance system. That's the brain. It tells the missile where it needs to go, how to adjust its path.
The brain, right?
Third is the warhead. That's the payload, the part designed to actually create the impact, the explosion, or whatever effect is intended.
Payload.
And finally, the control system. Think of this as like the nervous system. It takes the commands from the guidance system and turns them into actual physical movements, adjusting fins, nozzles, that sort of thing. It keeps it stable, lets it maneuver. Okay. So yeah, you can sort of think of it like a flying robot, a very specialized one. It knows its destination, knows how to steer, and knows when to complete its mission.
A flying robot that needs some serious oomph to get going. So let's talk about that initial part, the launch. It's incredibly explosive, right? We often see them launching from the ground, but they can come from anywhere, can't they? Like planes, ships. I know Israel, for instance, launches some missiles from fighter jets.
That's right. The launch platform can vary hugely. But what's truly astonishing is the sheer power involved. Right at ignition, the propulsion system kicks in, usually uses solid or liquid fuel. Solid fuel is, well, it's pre-packed, burns incredibly fast, generates massive thrust very quickly by expelling hot gases.
Like a giant, very controlled firework.
Kind of, yeah. Liquid fuels, on the other hand, you can sometimes control the burn rate a bit more, throttle them.
Yeah.
But either way, this isn't just a gentle push. It's an immense surge of power. We're talking speeds from, say, 3,000 up to maybe 15,000 kilometers per hour.
15,000? That's hard to even picture.
It really is. At the top end, yeah, that's crossing continents in under an hour. And the engineering challenge is getting that much power from something relatively small and light.
So it's not just fast, it's screaming through the sky.
Right.
Hypersonic, potentially. But okay, speed is one thing. The really mind-bending part for me, and maybe the harder part, is hitting a specific target maybe hundreds, even thousands of kilometers away. How on earth do these things, once they're up there, find their way so accurately?
Yeah, that's where the guidance systems really show their sophistication. Modern missiles use these incredibly advanced internal navigation systems. Often, it's a mix of technologies. You might have GPS, sure, using satellite signals, that's common. But really crucially, they often rely heavily on inertial navigation systems, or INS.
INS? What's special about that?
Well, what's fascinating about INS is that it needs no external signals, nothing from outside the missile. It uses these hypersensitive gyroscopes and accelerometers inside the missile itself. They constantly track every single tiny movement, every rotation, every change in speed, right from the moment of launch. So it's always calculating its exact position, updating constantly, even if GPS gets jammed or isn't available.
Wow. So it's like keeping its own internal map and tracking its journey second by second.
Exactly. A very, very precise internal log. And then you might also have radar guidance. The missile sends out radar pulses. It bounces off the target, and the missile sees where to go. Works day, night, bad weather.
Okay.
And all this data from GPS, INS, radar, whatever it has, feeds into the missile's control system. That allows it to make its own decisions, essentially. Adjust its fins or nozzles to turn, change altitude, speed up, slow down, all to stay perfectly on course for the target. It's this continuous loop of sensing, calculating, and adjusting. Real-time corrections.
Okay, so it's navigated the distance, made all these tiny adjustments. It's closing in. What happens in those final moments? How does the warhead, the payload, actually get triggered?
Right, the final stage. As it gets close, the warhead is armed and then activated by a fuse. Generally, there are two main types you hear about, a proximity fuse or a contact fuse.
Okay, what's the difference?
Proximity fuse uses sensors, maybe radar, maybe lasers, infrared, to detect when it's just near the target. Doesn't have to actually hit it. It detonates the warhead at the optimal distance. That's really useful for, say, airbursts against aircraft or troops in the open.
Ah, I see. And compact.
Contact fuse is simpler, in concept anyway. It needs to physically strike the target to trigger the detonation. Bang! So direct impact required. And once that fuse triggers, the warhead explodes. Depending on the design, you get different effects. Could be a massive blast wave, could be an intense fireball for incendiary effect, or it could be fragmentation, scattering shrapnel everywhere at high speed, designed for different kinds of targets.
It's all incredibly destructive, however it works. Now, given how much it's been in the news, we really should touch on missile defense. Specifically, Israel's Iron Dome. Feels like a crucial sort of bonus topic here, showing the other side of the coin.
Absolutely. And if we connect this to the bigger picture, Iron Dome is a fascinating example of defensive tech. It's an interceptor system designed specifically for shorter-range rockets, artillery shells, that sort of threat. The way it operates is just incredibly fast and precise. First, its radar spots an incoming rocket. Instantly calculates where it's heading, where it's likely to land. If the calculation shows it's heading for a populated area or somewhere sensitive, then the system launches its own missile, an interceptor missile called a Tamir. And the goal of the Tamir is to hit and destroy that incoming rocket right there in midair before it lands.
People often say it's like hitting a bullet with another bullet. Is that accurate?
You know, that analogy is actually pretty spot on.
Yeah.
It captures the sheer difficulty and precision needed. Think about it. You've got seconds from detection to interception. The system needs incredibly fast computers to calculate the intercept point and then guide its own small, fast interceptor missile to collide with another small, fast-moving object miles up in the sky.
How does the interceptor manage that?
It has its own advanced guidance systems, constantly getting updates from the ground radar, making tiny adjustments in flight. It's a combination of that rapid processing, the sophisticated guidance, and just fundamental kinetic energy, one fast thing hitting another fast thing.
Yeah.
Really is a remarkable piece of engineering. And it highlights this constant sort of technological chess game, doesn't it, between offense and defense?
It really does. So what does this all mean for you listening in? Well, hopefully next time you hear phrases like missile launch or ballistic strike or Iron Dome interception, you'll have a much richer sense, a more informed picture of the complex, powerful technology at play. It's easy to just hear the words, but understanding the mechanics, it adds a whole new layer. It's a mix of awesome and, frankly, terrifying ingenuity.
It is. And maybe this raises a question for you to think about. As these offensive missiles get faster, stealthier, maybe more maneuverable, and defensive systems like Iron Dome get even more precise, more capable, what does that continuous technological race actually mean for global security down the line? Does having smarter weapons on both sides lead to more stability, or does it just change the nature of the threat? It's this constant evolution, always pushing the limits of what's possible in engineering and physics. Something to ponder.